Okay, so we had done all these experiments, and we did establish that the force between two charges was proportional to the product of the charges and inversely proportional to the distance, square of the distance between the two charges. Now here, d is this distance. So if you have some charge over here, q, some other charge over here, q prime, this is the distance between the two. And the magnitude of the force is equal to the product of the charges divided by the distance squared between the two. Now, one of your friends were asking, okay, we know how to divide the charges, but what is the total charge to start with? I mean, here we also don't know what the total charge is. We only know that, for example, if we multiply the charge of the first one by some factor, the force also gets multiplied by the same factor. Or if you multiply the other charge by some factor, if we divide it by 2, divide it by force, the force is also divided by 2 and divided by the force. But what is the charge? So what would you like to have? Let's call it r squared this time. So what is the charge? One is what? I mean, you see, we know how to multiply charges or how to divide charges. But how do we define the unit of charge? I mean, you say, okay, 1, but what is 1? Well, we don't know electron, you know. I mean, at those times, we didn't know the electrons. Well, we don't yet know the currents. I mean, now the modern description uses the currents, but at that time, we don't know the current. But we want to measure it now. We want to define some unit. Remember when our discussions in the first of the mechanics courses, when we wanted to measure the distances, we just first established a unit. We said that, okay, this distance that we define in such and such a way is our meter. Now we have to do the same thing here. Yeah, I mean, choose a unit. What's the unit of charge? I mean, your friend had a point that I will come back in a moment, but let's say we can call, how did we create the charge? We said, okay, let's take this object, rub it on some other material, and if you do at the end of this procedure, you will end up having a charge. You can say, okay, you take the silk, take a amber of this size, a silk of this quality, you rub the amber on silk with such a force, exerting such a friction, creating such a friction force, this many times. At the end, the charge that accumulates is 1 Coulomb, or 1 Serjan, let's say. You can just define it like that. That is the definition of the unit of charge. It's in that sense, it's completely arbitrary. What is your unit of charge? Now, the traditional definition of charge, the traditional unit, the conventional unit of charge, I say not the traditional, the conventional unit of charge is 1 Coulomb. Now, this is proportional to, we have the 1 Coulomb of charge. Let's say 1 Coulomb. Now, if we measure charge in these units, then we can write the magnitude of the force between two charges is, we already know that it is proportional to this quantity, and the proportionality constant, let's just call it K. Now, sometimes rather than K, we use some other notation, 4 pi epsilon 0. And this number is, let's say, 8.99 times 10 to the power 9 newtons meter squared per Coulomb squared. Now, of course, you could have chosen some other unit of charge. Like now we know that the charge is nothing but the excess or lack of electrons or protons in a material. Well, because We know that the force is proportional to this expression over here. So you have to fix a proportionality constant. And this is the proportionality constant. By choosing our unit as 1 Coulomb, we are choosing this proportionality constant to have this value. I mean, you could have as well chosen that proportionality constant to be 1. But that would mean that the charge, the unit of charge will not be Coulomb anymore, but it will be just Newton meter squared square root. So that will be your unit of charge, which is equally valid. You don't have to use the Coulomb unit. If you change your unit, this proportionality constant changes. Just like instead of you using the meters for the length, you could have chosen to use the centimeters as your length unit. And if you use the centimeters as your length unit, this constant will again have a different value. So by fixing this constant, you are essentially fixing your units. Since we had already fixed the unit of distance in the mechanics, by choosing this proportionality constant to have this value, you are fixing the charges to be 1 Coulomb. Yes. Well, within experimental errors, it is too. I mean, experimental measurement always has an error. So we can never measure it to be exactly equal to 2. So let's say, suppose we have 1 Coulomb of charge, another 1 Coulomb of charge. They are separated by 1 meter. Let's say that I just hold these 1 coulombs at this distance. So what will be the force exerted on them? The magnitude of the force. Let's say here we have 1 Coulomb, here we have 1 Coulomb. They are separated by 1 meter, so the force that they exert on each other, the magnitude, 8.99 newtons meter squared per Coulomb squared, don't forget the units, times 1 Coulomb squared divided by 1 meter squared. This will be 8.99. Well, of course, here I have 10 to the power 9. Times 10 to the power 9 newtons. This is the weight of almost 1,000 tons. So I will not be able to hold them just like this. 1 Coulomb is a huge charge. So rather than using 1 Coulomb, what we use is 1 MicroCoulomb. This is 10 to the power minus 6 Coulomb. This will be mainly what we will be used in most everyday experiments. Let's do an exercise. We already have this piece of paper. I don't know if you can see it, just a small piece of paper. And we know that if we rub this ball sufficiently on a suitable cloth, I can just lift this piece of paper from, let's say, 1 millimeter distance. So let's just make many approximations. Let's say that the charge of this ball and the charge on this paper, they are more or less equal. So what is the charge? So the question just tells us that here we have some piece of paper which has a charge, let's say, Q. Here we have another piece of paper, not another piece of paper, but this ball. That has a charge, let's say, minus Q. And the distance between the two is somewhat like 1 millimeter. And then the paper just takes off from the top of the table. So what is Q? What is the charges that we generate by just rubbing like this? One millimeter, sorry. So what are the charges that we are generating? We already know the force. We know the paper. It's quite light. What do you think is the weight of that thing, the mass? Well, you cannot neglect it. 1 milligram. Do you agree? I would vote for 1 gram. Well, did you take any pills? Any medicine? No, you are such a healthy man. Not even a piece of painkiller. Well, those pills are a few grams. Gram is, I mean, or did any one of your friends get married? Or your relatives, did you buy a piece of gold? Now the pieces of gold, now they are selling 1 gram of gold. Well, in fact, you're right, this is much lighter than a 1 gram of gold, so 0.1 grams. This is the mass of this piece of paper. Okay, you convinced me. 10 to the power minus 2. Okay, this is the mass. So what is the charge? But this is the active material. I mean, it has the filling. Okay. No. I mean, this is just a notation. I'm just for the charge on these things, I use the symbol large Q or Q prime. Now it is the small q and Q prime. It's just a symbol that you use. I mean, if you want, just use the symbol A or B. I mean, are we that precise in our estimates here? Yeah, so I mean, taking the gravitational acceleration to be 10 would be good enough. So what is the charges that we have created? Let's calculate. Okay, what we did, we have this ball. I lost this piece. Here I have this piece of paper. This is the experiment I did. I just rubbed it a couple of times. I brought it very close to here, and when the distance was, let's say, 1 millimeter, the piece of paper just was lifted from the table. Okay? So given this information, and of course we will be making lots of simplifications, assuming that the ball and this piece of paper have the same charge, which is of course not true, but let's just make a simplification just to estimate. So with this information, what can you say about the amount of charge on this ball? That's the question. I mean, when they are equal, it will just be at the edge of the lifting off. So the weight of my object is 10 to the power minus 1 Newton. This is the weight. Well, this is just exaggerated. I mean, the weight will be smaller than this one. 8.99 times 10 to the power 9 newtons meter squared divided by Coulomb squared times Q squared divided by, the distance is 10 to the power minus 3 meters, so 10 to the power minus 6 meters squared. So these meters squared, they will cancel. These newtons, they will cancel. So the Q squared will be about 10 to the power minus 7, 16, 10 to the power minus 17, which 17 coulombs squared well, let's see, minus 1, minus 6, minus 7, minus 6, 16, divide by 10, 17. This is more or less 10. You're right, so this is minus 4. Minus 4. So this is minus 20. So the charge that we generate by just rubbing is 10 to the power minus 4 microcoulomb. Now this is more or less what you will get in your everyday life. Of course, under certain circumstances, when you get this electrostatic shock from the car or from by touching the metal, it will be a bit larger than this, but not that large. And this is the typical charges that you will experience. Now, any questions up to here? I don't really know. I mean, just as I was telling you, I also got curious, but I don't know the answer yet. Other questions? Well, I'm talking about the magnitudes, so this sign doesn't really matter. Now, since I'm talking about the magnitudes, I'm talking about the absolute values. So the sign doesn't make any change. But just since you have mentioned it, we already know that force is a vector. So we have to write the forces as a vector quantity, not just its magnitude, but its direction is also important. Now there, that minus sign will be important. So let's say we have this charge Q. This is the charge Q. I mean, you can use any symbol that you like. And here you have the charge, let's say S. And let's just call the distance between these two to be D. And of course, we need to talk about their positions. Let's say we have some coordinate axis. The position of this one, let's call it R1 or RQ. The position of, no, let's call it R1. And the position of the charge S is R2. Now the force acting on the charge at the point R1 due to the charge at the point R2, this is equal to, we have this K, Q1, Q2, R12 divided by R12 cube. And here R12, let's see, R12 vector is equal to R1 minus R2. So this gives the correct direction. Why the cubed? Didn't we say that it was the distance squared? Yes. And if you want to write down the magnitude of this thing, you have to write down the magnitude of R12, which is R12, divided by R12 cube. That gives me R12 squared. Or I can write the same thing as minus K Q1 Q2 R12 hat divided by R12 squared. Now this hat just means the unit vector. Now this R12 vector is pointing in that direction. So this is why I have this minus sign over here, because the force, no, hold on, I don't have the minus sign. Now, because if we have two of the same charges, the force has to be repulsive. If Q1 and Q2, they are, let's say, both positive charges, then the force acting on Q due to this charge S Yes, objections? Questions? Hmm? No? No, here, this one over here is the length of the vector. This one is the vector. Here. Here. No, this is the cube. Why? Well, let me write it explicitly. This thing is equal to KQS divided by R12 squared. This is the one you want to have, right? Times R12 divided by R12. But this thing over here, it's a vector whose length is 1. This is R12 hat. So if you, that is why I have this equality over here. This is not a unit vector. This is a unit vector, and here, as you see, you have this square. And as one of you were saying, should we have a minus sign or not? Well, you already know that if you have two of the same charges, they repel each other. So if Q1 and S, if Q and S, they have the same charge, that's if they are both positive or they are both negative, then the force acting on Q should be in this direction. Let's look at this vector. What is the direction of that vector? R12. What is the direction of R12? Towards the left or towards the right? R12 vector is towards the left. So if the charges are both positive, the force acting on one, the charge Q, or the charge at the point R1, should be towards the left. So there's no minus sign. So this is already a vector that is pointing towards the left if Q times S is a positive number. So I don't have a minus sign. Yes, it is R1 minus R2. Of course, this is equal to minus KQ with R21 divided by R21 cubed, which is nothing but minus F21. This is the force acting on the second charge, this charge, due to the first charge. So I have these two charges. they are exerting forces on each other. And so they satisfy the Newton's third law. The force that is exerted on charge 1 due to the charge 2 is equal in magnitude to the force exerted on charge 2 due to the charge 1, but opposite in direction. This is what this minus sign tells me, which basically tells me that these forces satisfy Newton's third law, and we know that if Newton's third law is satisfied, we have the conservation of momentum. So if there is any process which in which we have these electrostatic forces, that process will conserve momentum, which will not be always true. We will see towards the end. I mean, we will say that there is this, it satisfies Newton's third law, so if only the relevant forces that acts on your system are these kind of forces, we already know that momentum is conserved. Momentum of your particles are conserved. Any questions up to here? Now let's go back to the modern picture now. Yes? That is how I defined it. This is my definition. If you want to define it in a different way, you can just define it a different way. With this definition, this equation is correct. Now we already know that when you look at anything, it is made up of atoms. Well, whether it's a solid, liquid, or gas, it doesn't make any difference. It is eventually made up of atoms. But atoms are made up of electrons, we have the electrons which kind of orbit around what we call the nucleus. And nucleus is itself nothing but protons, some number of protons plus the neutrons. And we know that the electrons let's just, if we call the electron's charge as minus E, E is just, it should be minus 1.6 times 10 to the power minus 19 coulombs. Then the proton's charge is plus E. We have absolutely no idea why the electron and proton have the same but opposite charges. Why doesn't the proton have, I don't know, the electron charge over third? We don't know why. But what we know is that the proton and electrons, they have almost exactly the same charge. Within experimental errors that we have now, they have exactly the same charge. We don't know why. That is one of the things that we want to have an answer for, one of the questions we would like to answer. Why do the proton and the electron have the same charge? No, positron is something else. Positron is more like the electron with a positive charge. So if you look at an atom, it will have equal numbers of protons and electrons. So that then we say that the atom is neutral, because the charge of any matter, charge of an object, is nothing but the number of protons minus the number of electrons times E. So this is the charge of an object. For a neutral object, an object that doesn't have any charge, like the atom, the number of protons and the number of electrons are exactly equal. Now, what happens when you take some object and rub it on another object? like that piece of cloth. Now in that case, what happens is, since these objects are mainly solids, the nucleus, they tend to stick in solids. The nuclei, they are fixed at their position. They do not have so much flexibility. But the electrons are mainly moving from one substance to the other one. So electron from the, let's say this ball, is some of the electron is transferred to the cloth. So if the electrons are transferred from the ball to the cloth, then at the end of the process, we know that there are fewer electrons in the ball. So the ball is positively charged. This is a positive number. And the cloth will be itself negatively charged. And the number of electrons and number of protons, as far as we know, it's conserved. No matter what you do, what happens to the system, the number of electrons and the number of protons do not change in the system. Which mainly means that the total charge of a system will always be constant. It will be conserved. It is a conserved quantity of nature, just like the energy. We cannot create energy. We cannot destroy energy. We can only change energy from one form to the other form. And just like that, for the electric charge, you cannot create electric charge. You cannot destroy electric charge. But the only thing you can do is you can just change one type. You can just transfer electrons or protons from one substance to the other substance, creating some electric charge in that substance. But the total electric charge will always be conserved. Well, the total in the universe will always be conserved. So if, for example, this ball gets a positive charge, it means that somewhere else in the universe is negatively charged. Just like by rubbing this on the cloth, we are charging this ball positively, but the cloth will be charged negatively. The total charge will be 0. And in the atoms, the electrons are bound to, if you take a single atom, we have the electrons going around the nucleus, so they will be bound there. But when you start to put atoms together, things start to behave a bit differently. For example, in metals or in conductors, so if this is a conductor, these are your nucleus, like a piece of copper, let's say. The copper atoms will be fixed at their positions. For example, just copper atoms. Let's say these are the electrons. The electrons will be just moving around. In fact, they move quite fast. They're just free to move. So what happens if you bring, let's say, a positive charge? Let's say this is our conductor. We charge our ball positively. Now, of course, here we have positive charges. Here we have in the conductor, we have both positive and negative charges. All of them will be there. So the positive charges will be pushed away from, the positive charges in my conductor will be pushed away. The negative charges in the conductor will be pulled towards my ball. But the positive charges are fixed. They cannot move. But the negative charges can. The electrons are free to move. So what will happen is the negative charges will gather here. We will have an excess of electrons on this side, leaving behind, at this point, we will have less electrons, meaning the number of protons will be more than the number of electrons in this region. But that means that region will be positively charged. Here it is now neutral. It doesn't have any net charge, because the total charge will be 0. The only thing is that there are more electrons in this region. So this part of the conductor will be negatively charged, this part of the conductor is positively charged. Now, if you just take another conductor and attach it to the ground, you can think of ground as an infinite source of electrons. So that, I mean, you can take as many electrons as you like, it will still be almost neutral. You can give as many neutral electrons as you like to the ground, and it will still stay neutral. But then, if this is a conductor, the electrons are free to move in the conductor. Here we have some positive charges. These positive charges will attract electrons in this conductor. So the electrons will start flowing in this conductor until they neutralize these positive charges. So now, when we connected this metal to the conductor, what happened is the electrons now came to this point. Now we had a lack of electrons in this region. That lack of electrons is cancelled by the newly coming electrons. So this part is now also neutral. This part is negatively charged. This region is neutral. Now the electron has a definite charge. Now after this point, if you cut this conductor, if you cut the connection to the ground, and remove this positively charged sphere, my conductor will still remain negatively charged. So you can just, as a procedure, you can just imagine it this way. You have the conductor. You have the conductor. Then you bring a positive charge in the near vicinity, which creates some positive charges on this end, negative charges on the other end. Then you ground this thing. So now we have negative charges on this end still. Nothing happened to those negative charges, but the positive charges are cancelled by the electrons coming from the ground. Then you just remove the ground. It is still negatively charged. Now, if you now remove the sphere, you have a negatively charged conductor. So now, initially, your conductor didn't have any charge. Now it has some net charge through this process. So you have charged your conductor. Now, any questions? No, we didn't destroy the positive charge. What we did is we took some electrons from somewhere else. There were electrons over there on the ground. We just took them and brought it to cancel these positive charges. Now, effectively, we transferred this positive charge to the ground. But let's say if the Earth has one extra electron, all of Earth, we will not feel that difference. Yeah. From this part, nothing will change. Because the electrons will still be over here. They are pulled by this positive charge. Okay, see you on Thursday.